Good morning, dear, and welcome back. So, this is lecture 18, and today we are going to deduce a very important expression that is the logistic regression cost function. We'll try to differentiate. Okay, and from the first principle, this is very, very important. That's why from the first principle, we'll try to deduce it. Okay. In the earlier class, of course, you have seen that we have deduced a cost function for logistic regression. It's a very special function, isn't it? And intuitively, you have found out or invented the cost function, which is having the safe which we required. Okay, and then we can run the gradient descent algorithm on that cost function, and in that process we can evaluate the necessary parameters. So please pay attention, and I strongly suggest that prepare with your pen and paper so that once you can do this steps with me. And since you have a background in calculus, it is pretty simple. Okay, so don't worry. So fasten your seatbelt and let us move forward. So this was our cost function, beautiful separate cost function, and this cost function, as you know, has so many good names. This is called logistic regression cost function. Okay, this is a function which is convex in nature, where we will run the gradient descent algorithm. But here, the two log functions actually belonging to the two classes. Okay, this is my predictor. Just to recap, predictor, and this is my this is class 1. Okay, and this is the variation of the log function minus log h x parameters by w, representing this, and minus log 1 minus h x parameters by w is represented by this. And from very fundamental, these exponential functions actually were constructed here. What is that concept? That if my predictor telling the ground truth, no cost involved, zero cost, that means no penalty. But if my predictor is predicting something which is far from the ground truth, we will penalize, which is manifested in the increase of cost. And that's how these two functions, actually one function, these two part of the functions are evolved, and they crossed at a point, say 0.5 probability. That means here the entropy is maximum. Okay, and then that means if you are trying to see like this, say this is my x1, x2, and you have two classes. Say we have two classes, so we are trying to find a decision boundary here. Sorry about that. Okay, so and implicitly the h w xi actually is giving you the decision boundary, and decision boundary should be such, okay, which is passing through is called decision boundary because it should be placed at a place where any sample, if you calculate the probability if the sample belongs, if this is W transpose, actually W transpose X, equal to 0 is the decision boundary. So if it is greater than 0, so once you have that w transpose x for any sample, if it is greater than equal to 0, then you predict that okay, it belongs to class 1, or else it belongs to this class. So 0 class 1, in this is way the decision boundary is acting. So fundamentally, you see, we want decision boundary to be created at a place where it is very difficult to take decision, right? Decision boundary should not be here, because I know for this, then it will misclassify, because samples belonging to these classes, okay, will not be evaluated properly. So that's the reason here you need to understand that this is called cross entropy function. The two entropy are crossing over here, and this is the maximum entropy, and maximum uncertainty means maximum informations are there. We want our decision boundary to be constructed at a place where maximum information is there, so that our classification can be proper. Okay, so this is what we studied. Okay, and see, it's such a beautiful function we have now have. This is actually our cost function. This is our cost function for logistic regression, and it has several names. Logistic regression cost function, cross entropy function, because of this it is crossing. Okay, two classes are crossing, and our w parameters to be converged here. Okay, and it is also called log loss function, log livelihood function. So whatever you can see, they are basically the same. Now we need to differentiate this function, because now we will run gradient descent algorithm on this function. So on this function we will run gradient descent. That means for doing that you need to do that, right? So how to do this we are going to now learn. Okay, see, this is my cost function which we have derived. Minus sign is here, so this is plus, this is plus. Okay, be careful, this is very simple. Then we are substituting hx parameters by w equals to g of w transpose xi. Okay, so this is the logistic function, you know. So then we are getting here we are placing this, so we are getting this and this, nothing else. Okay, now again substituting z in place of w transpose x, we are substituting this equals to z. So then we can write down, okay, this after in terms of z, in terms of z. Okay, for simplicity we will omit sample sign here here onwards, but they are there. I am not putting it all this. Okay, so you know, okay, because we want cleaner looking expression. So this, and then I will have to differentiate this function with respect to z, okay, or z minus 1 by m. So with respect to z, if you differentiate, say log of gz will be 1 by gz, and then derivative of gz. So this is derivative of gz, okay, with respect to z. Then here also with respect to z we are differentiating, so 1 by this, so this is coming, okay, so this is coming over here, and then you will have minus g prime z, that is the derivative of this function with respect to z. Clear? So then simple math, okay, simplification. So So denominator will be like this. So then this multiplied by y g prime z, okay, plus this remains as it is. So this g z multiplied by minus g prime z. Okay. Now just taking common of so this remains y g prime z minus y g prime gz, then minus gz g prime z minus minus plus y gz g prime z. So here is one term y gz g prime z, here minus same term. So we are cancelling them. Okay. Just simplification. So up to this everybody is with me. Then further, okay, differentiating this. So this one, I am just picking up this two term. Here it is, and I am taking common g prime z. Okay. Now this is very interesting. That is very simple. Gz is a logistic function, 1 by 1 plus e to the power minus z. So how to calculate g prime z? That means differentiate this function with respect to z will be e to the power minus z 1 plus e to the power minus z whole square. Okay. This with a purpose I am writing. This is very, very important. Please note. Okay. Please note. What I am doing? I am writing this expression in terms of 1 by 1 plus e to the power minus z. So 1 is gone. There are two 1 plus e to the power minus z. Another I am tagging with this. Okay. This tagged with 1 plus e to the power minus z, and this 1 by 1 plus e to the power minus z has been separated. Okay. Now see the reason why we have done it. So this is exactly by definition our logistic function. So I am writing in place of this, okay, in place of this we are writing gz, okay, clear. And then again what we are doing, we are writing this expression as 1 minus 1 plus 1 minus 1 divided by 1 plus e to the power minus z. You see, you do this, you will get this. Okay, just simple math. But why we have written it? Because now the derivative of that logistic regression function can be written in terms of the function itself. Gz times 1 minus, this is again gz. This is very, very important. Always we use it. Okay, important. So differentiation of that function is equals to the function times 1 minus the function itself. That's very convenient for computation, isn't it? Now also from our substitution, okay, z equals to w transpose x, right? Because you see z equals to w transpose x. So I am writing this. So we can now differentiate this z function with respect to w, okay, and say wj, okay, in general. So then what will happen? Xj. Very, very important, very, very simple. Okay. And then from 3, from here and from here, we are getting derivative of the cost function with respect to z equals to, again simplification, y minus gz times, okay, now we see the derivative now, and derivative has been evaluated as this. So we are writing this in place of the derivative. So we are writing this, and So in the denominator and in the numerator you have the same. So they cancels out, and then you got 1 by 1 plus m y minus gz. Very, very important reduction. So from 5 and from 6, now we are reaching to the destination. So partial differentiation of our logistic regression cost function with respect to wj, that is parameter, is equals to calculating as this times this. Okay, you see. So both the expressions now we have, this is minus sign, sorry about small, so this is minus, please note negative sign. Okay, so minus 1 by m, summation of I equal to 1 to m, so y minus g w transpose x times x j. Okay, so this minus, when entering inside, we can write down 1 by m, summation of I equals to 1 to m. M is the number of samples, of course. Okay, g w transpose x minus y times x. Again, we are writing the samples because the operation is over. So then those samples are also everywhere, they were there, but to avoid clumsiness in expression, we avoided them. Now we have reintroduced them. Okay, so this is my desired derivative. So we have now the derivative of the logistic regression cost function. Okay, 1 by m, I equals to 1 to m. Okay, this minus this. So what is this? This is my predictor. So in terms of predictor, you can write this. So now you are ready to run gradient descent algorithm. Say batch, we are giving the example, but other variations also you can run. Repeat w j is the feature. Okay, assigned earlier wj minus alpha is the learning rate as usual. This is learning rate. This is number of samples, m h x parameters by w minus yi times xji. Okay. Now, if you just see the algorithm is this expression is similar, isn't it? But with linear regression algorithm. But as you now know that they are different. Why? Because in case of linear regression, this predictor was of the form w transpose xi, but here the predictor is of the form, it's a logistic function, w transpose xi. Okay, so that's the difference. Okay, now you know how the algorithm works. Now it will be very easy for you to implement this in suitable data set, which we will give. We have very two important, very simple data sets we have. Okay, so there are two classes actually, and through training data, level data, you will have to train. Train means you will have to determine these parameters. Okay, and once you determine the parameter, then classifiers are designed. Okay, because classifier will be w transpose t x greater than equal to 0 for positive class and less than 0 for the negative class. That means the decision boundary will be w transpose x equals to 0. W transpose, once you get w, so this will be our decision boundary, which you can calculate. And then, so this is a training process. Once the decision boundary is determined, then your design is exposed to testing. Okay, so any unknown sample, you bring it here, plug in there, okay, and it's if it is greater than 0, it belongs to positive class, less than 0 belongs to negative class. So that's it. You have now you are knowing very sophisticated, very important classifier which is known as logistic regression. Okay, it has special kind of cost function, because for any classifier you need what you need an objective function. Okay, so we have an objective function which we have derived. Okay, this is objective function. Intuitively we have derived, and then we have used it. Okay, we have used it for, that means we have differentiated this function, okay, in this form, differentiated this function in this form, and then we have used it for running our gradient descent algorithm. So again, same old story. If you have n number of features, then n number n, okay, n number of n as Nancy, n number of features, then n number of parameters will be there. So here you will have to, in the loop, you will have to have n number of parameters, and they will be have to be upgraded, tuned. W has to be tuned, okay, using same gradient descent algorithm, same gradient descent function we have, that convex function we have. So gradient descent algorithm we will run. Okay, so with this, the logistic regression main concept you know, and now you are ready to do assignments on this, which carefully designed assignments has been made available to you, and further hints will give how to solve those assignments so that you can digest what you are learning. But in the next class, we will also try to just show you that this is the function which we got. Is there a purely statistical interpretation of the logistic regression? We will try to answer that question in the next class, just like we did for linear regression. A linear regression cost function eventually proved to be can also be reduced from purely statistical point of view. Here also we will try to do that. Okay. Till then, stay safe and goodbye.